So, in interpretation of precipitation of data, so estimation of missing precipitation data at a station will be your first part of it. Okay, so let us understand why do we need to first estimate this missing precipitation, or else what is the need for doing this particular step. So how we'll do is first I'll go on reading the theoretical aspect, then we are going to have a discussion on what that particular sentences mean. Okay, so the first one is preparation of rainfall data. Okay, before using the rainfall records of a particular station, it is necessary to check the rainfall data for its continuity and consistency. So what do you mean by that? Imagine if this is your particular catchment area, okay, and you have, let us say, 3 rain gauge stations in this. Okay, as per the previous formulas that we have studied, that is your optimum number of rain gauge stations, right? So for n is equals to, we had that formula, right? So CV by epsilon squared, right? So based on that, if you determine what is the optimum number of rain gauge stations required, imagine that number comes out to be 3, okay, for this particular catchment area, and you have those 3 rain gauge stations already existing in the catchment areas. So now with respect to the optimum numbers that are required for to get that accurate rainfall data collected, so those requirements are done with. But now if I ask for this continuity and consistency, okay, so there are two things. One is continuity. So continuity in the sense, what if you are establishing these particular 3 stations in, let us say, in the year let us say 1990. Okay, imagine you are setting up these 3 stations in 1990, and you are collecting the rainfall data from these particular rain gauge stations every year, every month, every 6 months, every season, so based on your requirement. So at that point of time, all these 3 rain gauge stations which are there, that should give us the reading in every year. Okay, so imagine, so like this itself, if I can come and let us say for 10 years, okay, so this is 2000 year. Okay, imagine that. So at that point of time, what will happen is, so all the 3 rain gauge stations should provide us the values for rainfall data collected for all the years that will be enlisted over here. Now, due to some reasons, okay, some unknown reasons, imagine that middle rain gauge station has stopped working. At that point of time, how you are going to get the actual rainfall over the entire area? Because even if one station is not working, then its effective areas calculation you cannot do. The reason being what? How you will usually calculate this volume? Volume is equals to what? Depth of rainfall into the effective area, right? So at that point of time, if you don't have this depth for the middle one, at that point of time, you cannot calculate the total volume of rainfall that has occurred over there. And in turn, because of this, what will happen, even you cannot determine or predict what will be the rainfall data for this entire area, because that middle portion is missing. So at that point of time, what you can do is, we have certain methods or techniques with which you can actually take the help of the surrounding rain gauge stations who are here, and then you can actually determine what might be the readings of this not working rain gauge station. Okay, so that is with respect to the continuity value. Now the second thing, if when it comes, that is with respect to the consistency. So consistency indicates with what accuracy all these rain gauge stations are providing us the values. Okay, so what do I meant by that is, how much percentage of error is being shown by all these particular rain gauge stations. Because just giving a value of rainfall data collected is one thing, okay, that is with respect to the continuity what we spoke about, but with what accuracy those rain gauge stations are working, and with what accuracy they are what I can say, providing those data to the people who are working with this, so that is considered under this consistency aspect. So based on all the 3 steps what earlier in the previous slide what we have discussed, so based on that we are going to study with respect to the continuity and consistency part. Okay, so first let us check for test for continuity. Test for continuity. This indicates the continuous record of rainfall at a rain gauge station, which may sometimes be broken or damaged or fault in the rain gauge station, absence of the observer, etc. Such discontinuous data or missing data of a rain gauge station is established by using the rainfall data of the neighboring stations. So what does this mean? So if you check out, for what reasons do you think that a rain gauge station may stop working is because two things. One is if it is broken or it is damaged, one part, or if it has some kind of a fault in that rain gauge station. So you have seen in all the recording type of rain gauge stations we have a lot of moving parts and mechanical fixtures. So if any one of them is not working or if there is a fault in that particular instrument, so at that point of time your rain gauge stations will not work. Or else, one more important aspect is, even though the rain gauge station is working and it is giving you the correct results, but because of the remote location what it is placed in, so a person who is responsible to go there and collect the data may not end up there because of lot of practical difficulties. So even that's why they have given it as absence of observer. So absence of observer, it indicates what? It is not a mistake of the rain gauge station, but since the observer is not able to reach that particular rain gauge station at that prescribed time, so even at that point of time you cannot collect that rainfall data. So that's why even that is considered over here. So such discontinuous data or missing data of rain gauge station is established by using the rainfall data of the neighboring stations. That is, it is going to take the help of the neighboring stations and then you are going to get the value of that missing or discontinuous rainfall collected. Now continuing, in these calculations the normal rainfall is used as a standard of comparison. It is the average rainfall at a particular time obtained over a period of 30 years or a 3 decades period. It is called as normal annual precipitation if the average annual precipitation, if the average of annual rainfall is computed. So now here one important term that you need to remember over here is now onwards, okay, for all the calculations is this normal rainfall. So normal rainfall indicates what? Imagine if I have the same rain gauge station, let us say these three rain gauge stations are there, okay. So these three rain gauge stations, let us call it as 1, 2 and 3. Okay, if I collect the rainfall data of these rain gauge stations every year for next 30 years, okay, and if I average all that value, then that particular value I am going to call that as what? Normal annual rainfall. It is called as normal annual rainfall. So why this is particularly so important for us? The reason, because if you check out over the previous years, okay, so in a particular or in a one's lifetime, if I need to say, okay, if I consider that lifetime to be, let us say, around 70 to 75 years, okay, so at that point of time what will happen is the conditions of a particular area may change drastically. The condition of a area may change drastically. So what do I meant by that is, if you consider, let us say 1990, from 1990 till let us say this 2020, if I consider, okay, so 2020 if I consider, so within these 30-year period which is there, okay, so there might be a lot of changes that are happening to that particular area, and because of that even the rainfall pattern of that particular area will also may be changed. Okay, so if I just can take a simple example of Belgaum city itself. So previously, okay, in 1990s or in 2000s, so the quantum of rainfall that is occurring in that Belgaum area was I can say more above average, okay, but in the previous 2 years if you have just checked out, so the quantum of rainfall that has occurred has increased drastically. Okay, so why such things are happening? Because of the changes in the inhabitants, or else the changes in the environmental conditions that are going to occur in that particular area. This may be because of the development or any natural due to any natural calamities. If any of the changes are happening, so such kind of behaviors may be observed over there. This is just a small example, so it depends on again a lot of n number of factors, but from the point of what we are discussing here, why do we need this normal rainfall is because if I consider it for the last 30 years, okay, so at that point of time I will have sufficient data with me so that to understand what will be the rainfall characteristics for the last 30 years. Okay, that will help us for the further processing. Okay, now as I said, so these normal rainfall which is there, okay, and this is collected over a period of 30 years or 3 decades. Okay, and one more thing, it is called as normal annual precipitation if the average of annual rainfall is computed. So it is called as normal annual precipitation. It is called as normal annual precipitation whenever we are talking in terms of the average of the annual rainfalls. If you are not talking about the average of annual rainfalls, then it is just called as normal rainfall, and if you are talking with respect to the averages of rainfall, then you are going to call it as what? Normal annual precipitation. So this is the initial discussion for the test for continuity. Now in the next slide, we are going to check out with the three methods what we have to check for this continuity. Okay. So here, first one is what? Arithmetic mean method, or we call that as average arithmetic method. Okay, we have arithmetic average method or arithmetic mean method. So both term means the same. So let us read this particular section first, then we'll go for the next one. Okay, let P1, P2, P3 so on up to Pm are the annual precipitation values of M rain gauge stations, and N1, N2, N3 and so on up to Nm, and the Nx be the normal annual precipitation of the M station and the station X whose rainfall data is missing. When all the Ni's vary within 10% of Nx, then the missing station rainfall value is computed as the arithmetic average of all Pi's. Px is equals to 1 by m into bracket P1 plus P2 plus P3 so on up to Pm. So this is how you are going to calculate the value of missing precipitation. So let us convert this particular theoretical explanation into a figure. Okay, so imagine you have a catchment area. Okay, so in that you have imagine these, let us say for now let us have 5 rain gauge stations just for the sake of simplicity. So I'll call this as 1, okay, 2, 3, 4 and 5. Okay, we have 5 rain gauge stations with us. So at this point of time let us give some namings to those stations. Okay, so let us call this as 1, this is second, this is third, fourth and fifth one. Okay, so now with respect to this P1, P2, P3 up to Pm, so what this M is indicating is total number of rain gauge stations that are existing in the catchment area. I'll repeat myself, please check it out. M, just I'm not talking about Pm, okay, I'm just talking about this M value. Okay, so this M is indicating the number of rain gauge stations which are existing in the catchment area. So in our case right now this one is what? 5. Okay, keep that in mind. Now this P1, P2, P3, so what this P is indicating, basically this is what? Annual precipitation values. Okay, these are indicating what? annual precipitation values. So at that point of time, here if I write it, this is P1, okay, so this one is P2, here I have P3, here I have P4, and here I have P5. Okay, so now at this point of time, please check out, P is indicating what? It is just indicating that annual precipitation values. Okay, so if I consider any one particular year, okay, so that year rainfall data for that entire year will be represented by this P1, P2, P3 and so on. So all these values which are there over here, so they are going to give you the values of the annual precipitation. Now, what this N, N1, N2, N3 up till Nm. So what these N's are representing, if I need to write it down. So these are nothing but, yeah. So this N1 is indicating the normal rainfall for the station 1. N1 is indicating normal rainfall for the station 1. Okay, so what this normal rainfall is indicating as per the previous slide, so this is over a period of 30 years. Okay, over a period of 30 years the rainfall data has been collected from this station 1. Okay, and then that value what we are going to get is going to be called as normal rainfall. So it is not an average value, so basically it is a cumulative value what we are going to have. Okay, so if it is an average, so whenever it comes to the problems, so you are going to understand the value of P1 and N1, so both will be different. Similarly P2 and N2 will be different. The reason being what? P is indicating just that 1 year's rainfall data, whereas N is indicating for the last 30 years what kind of rainfall data that has. Okay, now similarly we'll have it for N2. Okay, then we have, sorry, we'll have it for N3, then we have N4, and lastly we have N5. Okay, now in this let us not forget one more thing, because here we have something else called as, just take green color. Okay, yeah, so this middle one right now what I have made is nothing but the station X. You can see this, it is the station X. So imagine for all these calculation I am doing for the year, let us say 2015. Okay, so I am doing it for the year 2015. So P1, P2, P3, P4 and P5 are indicating the annual rainfalls for the year 2015, and similarly N1, N2, N3, N4, N5 is indicating the rainfall data for the last 30 years from 2015. Okay, so keeping this in mind, now this middle portion what we have created over here, this station I am going to call that as X station. Okay, and whose rainfall data for the year 2015 is not available with us. I'll repeat myself. So the middle portion, middle rain gain station, the new one what I have added, I am going to call that as station X. And for this station X, the rainfall data for the year 2015 is not available. And with the help of this average arithmetic method, we are trying to determine that itself. Keeping that in mind, so next step what I need to do is, since I don't have the value of this Px, okay, I'll take some different color. Okay, I don't have the value of what? Px. The reason being precipitation at 2015 is not available, but this instrument has stopped working for this current year, because even for the previous years this particular instrument was working. So at that point of time I have the value of what? Nx, that is normal annual rainfall or normal rainfall for this station X. So already I have this Nx value, but I don't have the value of Px, and our job over here is to what? Determine this particular value of Px. Okay, so how you are going to do that? That is with the help of this simple formula. Okay, so what that is, px, yeah, so this px is nothing but what, the missing rainfall data, is equals to 1 by m. So 1 by m over here is represented by what, 5, not 6. Okay, you are not supposed to consider the station which is not working. Okay, so basically one more term if I need to introduce over here, here we call this P1, P2, P3, P4 and P5 rain gauge stations together, as we call them as base stations. We call them as base stations. Even though we have totally in this what I can say catchment area, total number of rain gauge stations are how much, 6, including this station X, the total number of rain gauge stations over here is 6, but for this base station we are going to consider only 5. The reason being what, one is not working and you are trying to determine the value of that not working rain gauge station. Keeping that in mind, so px is 1 by m, so that is 1 by 5 over here, into bracket p1 plus p2 plus p3 and so on. So p1, p2, p3 is what, nothing but this annual rainfall values with the green color what I have written. So that itself is going to be the formula for arithmetic average method. But now here if you can check out, there is no need of this n value. Okay, so for the further discussion or the further next methods, we require the value of these n's, so that time we'll discuss for that. But one more conditions that he had given is, when can you use this average arithmetic method is when all the ni's are varying within 10% of nx. So what do you mean by that? So if I try to explain with a table over here, let us call this as year. Okay, uh, next we have p value, here I'll call it as pi, and here I'll call it as ni. Okay, so let us call this as station number. Okay, so keeping this in mind, station number 1, let us say 1995. I'm just writing a random year number, that's it. pi is, let us say, 56 mm. Okay, 56 mm, imagine that unit is mm, and ni value is, let us say, some 650 mm. Okay, similarly second one for 90, yeah, so year is going to remain constant itself. Okay, so here let us say I have 75 and here it is 580 something. Okay, so similarly I have it for 3 as this is 95 only. Here let us say I have 63 and here I have somewhere around 700. Okay, similarly fourth one I have, this is same, 80, and here I have somewhere around 850 mm of rainfall. And lastly for the fifth station, 95 year, let us say this value is around 78 and here the value is around 760. Okay, now this is for all the ni's, so that is n1 to n5. Now we have one more value of called as what, nx. Okay, so if I take this nx, let us say this nx value is imagine 650. Okay, imagine this value is 650. Then what this particular statement actually gives you is, when you can use this average arithmetic method is whenever the nx or else all the ni's which are available with you, all the ni's which are available with you will vary within 10% of this nx. When you are going to use arithmetic average, I'll repeat myself again, when all these ni's are varying within 10% of this nx. Okay, so at that point of time, what is the variation of this 10% of nx? So we'll get a range with this. Okay, so 10% of 650 is what? It is 65, right? So here the total value is going to be what? 650 plus or minus 65. So what does that give me? So 650 minus 65 is going to be how much? That is 585. So here I have one lower value as 585. Now similarly 650 plus 65, 650 plus 65, it is going to be 715. Okay, 715. So what does this give me is, it is going to give me a range. Okay, so if all the NIs which are available with me in this table, if all the NIs are varying from 585 to 715, then I can go ahead and use for this average arithmetic method. Okay, so all these data right now what you are seeing in terms of this table, okay, will be available to you in the question. So whenever we solve the problem, so such kind of table will be given to you. Okay, so if this all the NIs are basically varying within this range, then you can basically go ahead and use this method. But right now if you check out our case, we have one value 850, which is more than 750, so it is not in this 10% range. So with that I can say, we have n number of here, even if 580 is not there, even 760 is not there. So three values out of five values are not within this range. So keeping that in mind, so I cannot use this average arithmetic method for this given set of data. I hope you understand. For this given set of data, I cannot use this arithmetic average method. So for that, we need to go for normal ratio or multiple regression method. But for the sake of explanation, whenever it comes to the problem solving part, so you need to make sure that all the NIs needs to vary within 10% of NX. Only at that point of time, you can go ahead and use this average arithmetic method. Okay. And regarding the problems on these, we'll solve it in the once we complete all the theory part for these problems. Okay.